Hello students. Let's continue with this lecture on the three input NAND gates. So what we are trying to look into is a three input NAND gate schematic, drawing the three input NAND gate schematic, and then appropriately find its propagation delay falling as well as the rising delay. In this particular aspect, because there are multiple transistors which are connected in parallel and then series, especially in series, we'll have to use the Elmore delay method or the Elmore delay model to evaluate or to arrive at the propagation delay falling or the rising parameter. Right. So just so this is particular schematic of a three input NAND gate. So the three input NAND gate. By definition, what we are going to do is design the three input NAND gate such that its rising and then falling resistance is equal to that of the unit inverter. Right? Unit inverter's rising and falling resistance, whatever is the unit inverter's rising and falling resistance is, we are going to match that with that of the three input NAND gates rising and falling resistance. Right? So what it means is, so for a three input NAND gate, so I have given the inputs A, B and C. So this is my inputs A, B, C, and then A, B, C on the pull down side and then on the pull up side. On the pull up side, we have this PMOS transistors, three of the PMOS transistors in parallel. And on the pull down side, we have this three of the transistors in series, right? And this is my output node. So for falling output, what we need is an output node y should go down to 0. So that is the falling output. So it will start from 1 and then it will do the transition from 1 to 0 and then it will reach a steady state of 0. So that's what the falling output is. During this particular falling output, what we want is an equivalent resistance of R. Right, the R equivalent resistance of R is coming from the unit inverter's falling resistance. Right, so if I consider the unit inverter, when the output is actually falling, the NMOS transistor, gives us the switching resistance, which is nothing but the falling resistance. So if I use a unit inverter, which is 2:1 ratio, I know that the switching resistance for the falling output is nothing but unit R. And similarly, if it is a 2:1 inverter, the switching resistance for a rising output is also R. Right, so in this case, for a three input NAND gate, all the three transistors has to be operating, has to be on, and that is when only we will get the output to be discharged to 0. Right, so in that case, if all the three series transistor has to be and the equivalent of all these three resistance should be equal to R, that means I can have individual transistors giving a resistance of R by 3, R by 3 and R by 3. Right, so the individual resistance, I can say that it should give me R by 3, it should give me R by 3, and then if it gives me R by 3 here, switching resistance, then the equivalent, the total of this three transistors switching resistance will be R. Right, so the R effective, I'm saying that should be equal to that of the unit inverter's falling output switching resistance or the falling resistance. So the individual NMOS transistors for the three input NAND gates, in the pull down side, the three input NAND gates will give me three transistors in series. So that's why the individual NMOS transistors is R by 3 is the switching resistance. On the rising side, it is slightly different. On the rising side, for the three input NAND gate, one of this PMOS transistors has to be on, right? And if the other two are off, that's okay, because output will get charged through one of the on transistors. So the three transistors are in parallel. If the two transistors are off, the other leg is on, other transistor is on, and then it will get charged from the output will get charged through the on transistors, which is connected to the VDD. So in that case, A or B or C transistors can be 0. That means that the transistors will be on in the PMOS side, giving an input of 0 represents that the PMOS transistor is on. R effective in that case should be equal to that of the R of the inverter. So the individual PMOS in that case should give me a switching resistance of R. Right. So what we are doing is in the pull up side, so I'm just taking a pointer. So in the pull-up side, we are taking the worst condition. We are taking the worst condition to design to get to the equivalent resistance, right? And the worst condition is when one of them is on. When all of them is on, actually in the pull-up side, when the PMOS transistor A in parallel with the PMOS transistor B in parallel with the PMOS transistor C is on, effectively my resistance in all of them will be in parallel, and then my equivalent resistance in the pull-up side will be very, very less. Parallel resistance, right? So a very less switching resistance will give me a very less delay, right? R into C will give me a very less delay, right? And which is very, very good for our digital circuit. What we really want is we want to estimate for the worst case condition. So worst case, timing condition is when A will be, the signal for the A arrives, but B and C doesn't arrive at all. So in that case, what is the propagation delay? In that sense, we wanted to find out for the worst case condition, right? Still, our resistance for the pull-up side should be equal to that of the resistance of the pull-up side of the unit inverter. And hence we have taken one of the conditions, one of the input conditions or one of the transistors on the pull-up side to be on. Either A will be on, or B will be on, or C will be on, right? Considering that, we need to have it equated or expressed or make it equal to that of the unit inverter's pull-up side switching resistance, right? So in that sense, the individual PMOS transistor, we are saying that it will be having a resistance of R. Hope you have understood that. Moving ahead. So what should be the width of the 3-input NAND gate in that sense, right? So on the NMOS side, on the pull down side, we know that all the 3 transistors which are in series has to be on, and then only the Y output will get discharged to 0. So all the 3 transistors on the NMOS side has to be on, and we had said that each of these transistors should have a resistance, individual switching resistance of R by 3, so that finally we will get a switching resistance of R which is equal to that of the unit inverter's falling resistance, right? So if it is R by 3, then my width has to be 3, so that I'll get a resistance of R by 3. Similarly, the second transistor, the B transistor, should also have a width of 3. The C transistor should also have a width of 3, so that I'll get the switching resistance of R by 3. On the pull-up side, on the PMOS side, one of the transistors will be on, the other 2 will be off, and in that case, my equivalent resistance should be that of matching with that of the unit inverter's rising resistance, right? The unit inverter's rising resistance is R on the PMOS side, and if one of them is on, the width, if I consider A to be on and B to be off, right, and C to be off, in that sense, the resistance here should still be R, right, on the PMOS side, right? So the width here for the 2:1 inverter was 2, which will give me an the switching resistance or the rising resistance as R. Therefore, the width here for the 3-input NAND gate on the pull-up side should also be 2, right? A width of 2 for a PMOS transistor will give me a resistance of R, right? So that's why transistor A, I have written the width of 2. For transistor B, when it is on, when this one will become on, so when this one will become on, and then A will become off, and then C will become off, right? In that sense, I will have to have a width of 2, so that it gives me an equivalent resistance of R. Finally, for C, right, if B and A are off and then C is on, I should have a width of 2, so that it will give me an equivalent resistance or rising resistance of R. So that implies that all the 3 transistors on the pull-up side should have a width of 2, so that individually they should be able to give a resistance, a rising resistance of R, right? For the worst case condition, what we are assuming is one of the inputs will be on, the other 2 will be off. Right, hope this is clear. So the dimensions or the design of this particular 3-input NAND gate is now clear because we have done this width or the dimensions scaling in such a way that it will give me an equivalent resistance on the pull-up and the pull-down side equivalent to that of the 2:1 inverter. Moving ahead, so if I have this particular scaling on each of these transistors, we need to understand what is the capacitances associated with each of these transistors, right? So the capacitances, there are three capacitances: the gate capacitances, the depletion capacitances, or the diffusion capacitances. So put together, I have detailed it out. I have made all the capacitance arranged except this non-switching capacitances, right? Non-switching capacitances is this capacitances. So I have to put 2C and then VDD here, right? So this terminal is also connected to VDD, and on the other side it is also connected to the VDD. So I have not taken this into account. Similarly, there will be one capacitances here, there will be one capacitances here, which will not switch based on the changes in the input or the changes in the output, right? As the input changes, the output should change. But this non-switching capacitances on each of these transistors on the PMOS side, and on the NMOS side, we will have a C transistors which will have one non-switching transistor here. On both the sides it is ground, so this we will not we will not accommodate or incorporate in our design, right? Because that will not have any effect on our calculation of the delay, because on both the terminals we have the DC source. So that is something I have not accommodated in this particular diagram. We have the gate capacitances. So the gate capacitance is much easier to understand. If the width is 2, the gate capacitance sees a capacitance of 2C. The gate capacitance from the B of the PMOS is 2C, and then the gate capacitance on the C transistors on the pull-up side is 2C. The gate capacitances on the pull-down side for a transistor of width 3 is nothing but 3C, 3C, and 3C. This is the gate capacitances. So remember that this input A and then this particular input are actually tied together, right? Input B, this particular input, and then this particular input on the pull down side is tied together, and on the C input and the C input and then the C input on the pull up and pull down side are tied together. So the input as such, if I'm talking about the input A, it sees an overall capacitance of 5C. Right, so this actually sees a capacitance of 3C plus 2C, which will be 5C. Right, similarly, the B input also sees an overall capacitance of 5C, and C input also sees an overall capacitance of 5C. Okay, so on the input side, it is clear now. Now let's accommodate, or let's try to understand the diffusion capacitances in this particular circuit, or the parasitic capacitances. So the PMOS side, there will be two diffusion capacitances for the transistor A here. This being a non-switching capacitance, so we are not going to write, or we are not going to worry about it. There is one which is connected to the output node here, right? So this becomes the drain of the PMOS transistor, and that will be the 2C with respect to the body. Body is connected to the VDD, and for our transient analysis, any kind of a VDD source, a DC source, we will make it ground. So that's why we have this 2C capacitance. So this is coming from the depletion capacitance of this particular transistor. There is one more 2C coming from the B transistors. 2 is the width, so I will have the 2C capacitance here. And then the C transistor will give me one more, because its scaling is 2, it will give me a 2C capacitances here. Right, so overall on the pull up side, right, the pull up side is contributing 2C plus 2C plus 2C, which is 6C capacitance connected to the output node, because all these drain terminals of A, B, C are connected to the output node terminal Y. All right, now coming to the pull down side, I have transistor A, I have the transistor B, and I have the transistor C, which are connected in series. All these transistors also have the depletion or the parasitic or the diffusion capacitances associated with its terminals, drain and source, with respect to the body. So if I consider this, the transistor A here on this particular side, which is the drain side, it incorporates, or it shows a capacitance of 3C here, because the scaling is 3, so it will have a capacitance of 3C connected to the body, which is nothing but grounded, right? On this particular side, so if I consider this to be, let me take a different color. Yeah. So if this is the drain, and then this is the source, and this is the drain, and then this is the source, this is the drain, and this is the source. All right. So the drain to body capacitance 3C we have seen, and source to body, I should have another 3C capacitance for this transistor A. And for transistor B, the drain to body should also have one more capacitance of 3C. Right? So in this particular node, in this particular C and D, which is basically a merged node, merged diffusion, merged node as such, coming from the transistors A and B, so coming from the transistors A and B here, I should get here, instead of 3C, I was expecting around 6C capacitance, because one 3C is accommodated from the source to the body capacitance coming from the transistor A, and another one is the drain to body capacitance, coming from the transistor B. But I have stated here 3C capacitance. Right? Similarly, on the another node, transistor B, source to body, and transistor C, drain to body, I was expecting around 6C capacitance, but I have written it as 3C. Alright, so that is something we will have to look into it. And I'm saying that this is nothing but a merged diffusion uncontacted capacitance. Right, so what I'm saying here is, because of the diffusions being merged, right, the transistor A, B, and C are in series. So the source diffusion of the transistor A gets merged with that of the drain diffusions of the transistor B. So I will have only one diffusion now of the width of the 3 size. So that's why I'm writing it as 3C instead of two separate 3Cs, making it as a 6C capacitance. Similarly, for the transistor B, the source to body, and then the transistor C, drain to body, I should accommodate 3C and 3C capacitance, but I'm writing it as, it should have been 6C capacitance, but I'm writing it as 3C because I'm saying that this is a merged diffusion uncontacted capacitance. So that means the drain of one transistor and then a source of another transistor are actually merged together and giving me a single pocket diffusion. Right? So at this particular slide, the overall capacitance has been drawn. The gate capacitance is kind of clear to understand. This particular drain to body capacitance is clear to understand. And there is two more merge diffusion capacitance, which we will see in detail in the next slide. So to come back to this Y output node, right? So the drain to body of this transistor A on the pull down side is going to contribute to 3C, and the pull down side is going to contribute 2C plus 2C plus 2C, which is 6C. So overall, the output Y node of this particular individual stage sees a capacitance of, right, 3C coming from the pull down side plus 2C plus 2C plus 2C, right, coming from the pull up side. So overall it sees a total capacitance of 9C. Right, hope this is clear. Okay, now what do we mean by this merged diffusion capacitances, which we had seen earlier, which we had seen in the last slide? It is nothing but talking about this 3C and then this 3C. So if I draw the cross-sectional diagram of the pull-down circuit of the 3-input NAND gate, this is what we will get. Right? On the A side, I will have, okay, I think this is slightly wrong in the sense, so this should be A. So this is drain. This is source, this is drain, this is source, this is drain, this is source. Okay, on the pull down side. So this is my pull down circuit of the 3-input NAND gate, and this is a cross-sectional diagram. So this is A, B, and then this should be C. Right? On the A side, there is a drain diffusion, which is nothing but the output node Y. Okay. On the other side, it is the source diffusion, and then the B. We have the B transistor, B NMOS transistor having the drain diffusion. So both the diffusion pockets are nothing but the same. It is merged diffusion. So I will not have two separate diffusion pockets. So I will have only one diffusion pocket here, which will give me a capacitance of 3C. Similarly, on the other side of the B, so it is a source here of the other side of the B, and then the C transistors, the drain diffusion. So both of them will get merged, and then will give me the 3C capacitance. All right, so that's what we had said. So if I were to draw two diffusions, right? So if I were to draw two diffusions for the B transistors, so if I'm drawing it two separate diffusions here, B and right. So this is for the B transistor, and then this is coming for the A transistors. What is likely to happen is, so the width will be 3, right? So I will have this. So the overall footprint is going to increase because now I have two diffusions. Instead of merged diffusion, if I have an unmerged diffusion, showing two different diffusions for B and A, but also it is connected because I need this particular node. This particular node is anyways connected. So I need to have this and then have this connected by a metal line or something like this. All right. So it is an unnecessary metal line coming, or it is an unnecessary area that is being consumed. In addition to having, instead of 3C, I'm going to have, this particular diffusion is going to give me 3C, and then this particular diffusion is going to give me 3C. So it is going to add to my capacitance, which will be 6C capacitance, right? And then 6C capacitance is likely to take more time to charge till 50%. So, halfway point. So the overall delay is also going to be increased. So my performance is going to drop if I have two separate diffusions. My area is going to be more because of two separate diffusions of the same width. And then lastly, I will have to have one more metal line which is going to connect both of them together. So all these three, is making our design inappropriate. In the sense, I wanted to optimize it over performance, over the footprint, over the area, reduce the processing steps as well. Right? Any additional processing steps is likely to take more cost. So in that sense, putting all the three apart, if we can have a single merge diffusion, that's what we have drawn here, it will take away all those things and make our design a little bit more optimized towards the performance, towards the area, right? And then towards the steps also. So in that sense, we have this merge diffusion capacitance. So wherever you see the series transistors, we will have the merge diffusion capacitances also, right? So even in an 3-input NOR gate or a 2-input NOR gate, we will have two of the PMOS transistors connected in series. So whenever you see it, whenever we see a series transistors, we will have a merge diffusion uncontacted capacitances, right? Uncontacted represents that, so this is called uncontacted because there is no metal line here which is connecting. So what it signifies is we are only interested in the output of this particular 3-input NAND gate connected to some other circuits, right? We are not interested in this connected to any other circuit. So that's why there is no metal line that is, that is flowing along this particular diffusions, right? So this is not there. We have only this output connected to the another part of the circuit, right? And that's why it is called as an uncontacted merge diffusions. Okay. Proceeding further, so now I have the sizes, now I have the capacitances, now I have the capacitances seen at the output node Y, which is 9C. I have the gate capacitances, which is nothing but, overall the pull up and pull down side for the individual inputs turns out to be 5C. And then I have the merged capacitance, which is nothing but 3C and 3C. So I should be able to find out what is the falling output, what should be the propagation delay for the falling for the 3-input NAND gate. So I've drawn an equivalent circuit here. All A, B, and C should be 1, then only the output will discharge to 0. Then only the output will discharge to 0. If I have all the A, B, C to be 1, that means all the transistors should be on. On the PMOS side, if A, B, and C are 1, all the transistors on the PMOS side will not be operating at all, right? Although it's capacitance of 2C here, right? The capacitance of 2C here is anyways there. 2C here is anyways there, which will get incorporated into the Y, and that's why I've written the Y as a capacitance of 9C. So all this 2C, 2C, and 2C, and then this particular, there is a 3C capacitances here also, which is accommodated into the 9C capacitance. This 9C capacitance has to discharge completely to 0, right? And that is when we will find out the propagation delay falling. So using the Elmore delay method, what I've drawn is the source is now ground here because it is discharging. And then we have drawn, this is the ground here. So this is the source. The resistance closest to the source is nothing but the switching resistance of the transistor C. So that we have the switching resistance of RC. The next node capacitance is nothing but 3C, so that's what I've written 3C here. And then we have the switching resistance of the transistor B, which is RB, and then the node capacitance is 3C. The next resistance is the RA resistance, switching resistance of the transistor A, and then the output node Y, which sees a capacitance of 9C. So this is my overall RC circuit. The three RC circuits which are cascaded together, and here we should be able to apply the Elmore delay method to find out what is the overall propagation delay falling for the Y output. So the region of interest, so my node of interest is Y, and each of this capacitance has to be accommodated. So I'm going to write 3C capacitances, which is nothing but I'm considering this capacitances. I have to find an equivalent capacitance seen for this 3C. Alright, so there are, I need to find out the shared resistance. So the shared resistance for this particular 3C capacitances plus, this particular 3C capacitances. And I need to find out the shared resistance for this particular 3C capacitance, and finally this 9C capacitances, and then the shared resistance for this 9C capacitance. So this is what I need to find out, which will give us the propagation delay for the falling output. Right? Hope this is clear. So the shared resistance for the 3C capacitances here, will be, because it's a shared one, we need to identify two paths. One path is from the source to the output. So it will be RC plus RB plus RA. That is one path. The second part is with respect to the individual nodes where the capacitances are seen. So I will have this 3C. So from source to 3C, this capacitance, I will have only RC as a component. So the common between the two paths of resistance is nothing but RC. For the next node, I have this RC plus RB plus RA as one path resistance, and then from source to this particular 3C capacitance, I have now RC plus RB. So the shared resistance is now RC plus RB. And finally for 9C, 9C sees from the source to the 9C node, the node Y, I see a resistance of RC, RB, and RA. So in its the output node to source path also gives me RC, RB, and RA. So the overall resistance here is RA plus RB plus RC. Right? So that's what I have. So the Elmore delay method, the shared resistance, and then the individual capacitance is what is written. And so that's what, RC and then RC plus RB plus, and then finally RC plus RB plus RA. So RC individual, resistance is RC, RB, and RA are nothing but R by 3. That is coming from the switching resistance of the NMOS transistor, which has a width of 3. So each one of them is R by 3. And RA is also R by 3. Right? So in that case, I will have 3C into R by 3 plus 2R by 3 into 3C plus R into 9C. So this 2R by 3 is coming from RC plus RB. And then this particular R is coming from RC plus RB plus RA. So finally, I will get 12 RC as my propagation delay falling, assuming the inputs are not a step input. So it's a very conservative approach. So that's why we have not used any log of 2. So hope this is clear. The falling output is clear. Next, we have to find out the rising output. So for the rising outputs, because there are 3 transistors on the PMOS side which are in parallel, so what we can have is 3 different combinations, right? Either one of the, we can have in fact 7 different combinations where, one of the transistors, the first 3 combination could be the one of the transistors is on, the other 2 transistors are off. And then the next 2 combination could be 2 of the transistors being on, then the other one being off. And then the last one, so the 6 combinations, overall 6 combinations. So the 6th combination is when all the transistors will be on the PMOS side. Out of the 6 combinations, right, the first 3 combinations is likely to give me a larger delay because only one transistor is on. If any 2 combinations or 3 combinations are on, the overall equivalent resistance will be smaller because all of them are in parallel. So in that sense, if I have only one transistor being on, so the first 3 combinations where one of the transistor is on, so that we will consider and then see what is the output. What is the propagation delay rising? So I've written case 1 where A is equal to 0 and then B and C are 1. So A is equal to 0 represents that on the PMOS side it is on, right? So this particular transistor on the PMOS side is on. The other two PMOS transistors on the pull up side is off, right? And on the pull down side, this is 0 represents this is off, and the other two is on, right? So other two is on, but this is off. What it means is the connection between the output node to the next diffusion is off. So I don't have to worry about this 3C capacitance and 3C capacitance being charged, right? Because this charging path for this particular 3C capacitance and then this particular 3C capacitance, right, through the VDD path, right? If I want to charge this, so I have to have this particular path. So the 3C should get charged, right? But this path, because this transistor is off, so this path is not there, so that there is no channel there. Hence, this 3C capacitance and then this particular 3C capacitance and this particular 3C capacitance is not likely to charge at all. What is likely to charge is only this 9C capacitance. And the 9C capacitance is going to charge with a propagation delay rising will be nothing but 9C into the switching resistance of this transistor, which is R. So I will get 9RC, right? So considering this as the first case where A is equal to 0 and B and C are 1. What if I have B is equal to 0 and A is equal to 1, that means there is a channel existing. So there is a channel existing for A, but B is off, that means that this 3C will be able to see a channel for charging. So this 3 will also has to be charged now, right? So in that sense, in the second case, I have A is equal to 1, B is equal to 0 and C is equal to 1. So that means A is equal to on, C is equal to on, but B is equal to off, right? So now I have this 3C getting a path to charge, but my output node of interest is only this, all right? So according to the Elmore delay, what we will have is this 9C, right? This 9C multiplied by the shared resistance, which will be nothing but the switching resistance of the transistor B on the PMOS side, plus I will have 3C, right? This particular 3C, which now sees a path through the transistor A on the NMOS side. The switching resistance of the NMOS side is nothing but R by 3. And then the switching resistance of this pull-up side B transistor is R. But because my node of interest is only Y, the common shared resistance path is nothing but the B transistor of the PMOS switching resistance, which is nothing but R. Put together, I will get 12 RC. So that's what I have written here. Right? Hope you have understood this. According to the Elmore delay method, right? Even though it sees a channel here, the output node of interest is Y, so the shared resistance is nothing but of the switching resistance of this B transistor. Right? Case 3, when A and B both are 1, that means, and C is 0, that means this is on. This is on A on the pull down side, and then this is on the pull down side, and this is off. So now I will have this 3C as well as this 3C now sees a charging path for the VDD, for connecting to the VDD source, right? So the overall, so the Elmore delay I have written for the charging. So the source is VDD, but this node, Y node, is my interest output node. I will have RC of PMOS as the switching resistance, and RA and RB connecting to the 3C and 3C capacitance on the NMOS transistor. So this is the NMOS transistor, which I have stated here, and then this is the RB is the NMOS transistor, which connects to the 3C capacitance here, right? So the shared resistance for this particular capacitance is nothing but still the RC PMOS, and the shared resistance for this 3C is also the RC PMOS, because my output is, the Y is my output node of interest. So I will have the propagation delay rising as 9RC plus 3C into R plus 3C into R. So basically 9C into R, this particular R, right? So 9C into this particular R, and then 3C into this particular R, and then 3C into this particular R. Right? Overall, I will get 15 RC. So this is my worst case, the maximum delay I will get because of this particular combination. So I'm going to consider this in my characteristics for a 3-input NAND gate, right? Because we will always design our gates at a transistor level such that I will get the worst case condition to satisfy the timing constraints or the timing requirements, right? So in that sense, I will have a propagation delay falling and propagation delay rising. So the propagation delay rising for a 3-input NAND gate turns out to be 15 RC, and the propagation delay falling, it turns out to be 12 RC, right? As per our previous slides. Right, so hope you have understood this. This lecture. Very important to understand the 3-input NAND gates. How do we design the width, and how do we apply the algorithm method to find out the worst case delay? In this particular combination, the worst case delay turns out to be on the rising side, and 3-input NAND gates on the rising side, we get the worst case delay as 15 RC. The falling delay, all the 3 transistors for a 3-input NAND gate has to be on. So there is no worst case delay on the falling side, because all of them has to be on. Otherwise, it will not fall. It will not discharge to zero. The output will not discharge to zero, and thereby all the 3 transistors has to be on, and then we will get the falling delay has to be 12 RC.